we're moving into chapter 8 now. Chapter 8, chapter 9, and I think a little bit in chapter 10. So, let me kind of break down what we're doing here. We have, before the week of final exams, we have 3 weeks left. So there's 6 classes left. In that 3 weeks, we have to do, in chapter 8, we're going to do applications today. Okay, applications of trig functions. And then we're going to do the law of sines and law of cosines. The applications are word problems, okay? So that takes some interpretation. Law of sines, law of cosines are very calculator-intensive problems. They're very useful if you plan on going into engineering of any sort. Chapter 9, we only do 2 things. We do vectors and polar coordinates. Right? So we'll do polar first, and then vectors. These are very useful if you have to take any sort of physics. Right? You need both of these. And then chapter 10, we're supposed to do 2 things. We'll see if we get to both of them. Conic sections and parametric equations. And all the times that I've taught 127, which is like 10 different semesters now, I've never gotten to this. I don't know why. I just can't seem to get to it. So maybe this semester will be the semester. I mean, we have 6 days and we have 6 things to do, but I highly doubt it. All right, most likely, I'm going to have to let you guys study this on your own. It doesn't come back again in math until calculus 2, in which time you have to review it anyway, but hopefully we get to it. If not, then not. But this is what we have to do. This is what we have to do.
Will we have to study on our own for the test?
I won't put, if we don't cover it, I won't put it on the file. So you guys got calculators today, so you can help me? Andy?
Yeah.
I'm too busy to actually put things in the calculator. So the applications that we're going to do today cover 2 sections. They start at 8.1, and then they continue in 8.5. And there's a whole bunch of different types of applications of trig functions. But we're going to focus on 3 particular ones. We're going to solve right triangles, which we've done a little bit already, so shouldn't be too bad. We're going to solve problems involving bearings. So bearing is like the direction that something's heading. And then finally, we're going to do simple harmonic motion.
Sounds pretty.
I know. It is. So these are the 3 things we'll cover in 8.1 and 8.5. These 2 are in 8.1, and then this one's in 8.5. Now, so we'll start with solving right triangles, which, like I said, we've talked about a little bit, so this should go quick, but now we're just going to have to use, make sure we can use our calculators to get these answers. To solve a right triangle means to find the missing information. Okay? So what will happen in a lot of these examples is you'll be given either with a picture or with words some description of a right triangle, and you have to solve for anything you don't have. So for example here, in the right triangle below, angle B is 70 degrees and C equals 10, solve the triangle. So I give you a right triangle. I label it for you A, B, C, A, B, C. This is a labeling you should get used to. There's kind of a pattern to this, meaning that capital A, all the capital letters are angles, represent angles, and all of those how do I put this? The capital letter and the lowercase letter are opposite one another. Now, this isn't always necessary, but it's kind of a standard labeling you'll see in a lot of books, just so that you don't even need the picture, right? You could get the picture on your own because you know that capital A is always across from lowercase a, and capital C is always across from lowercase c. So I'll talk more about this when we get into law of sines and law of cosines, but there is kind of a logic to the way this is labeled. All the angles of the capital letters and the lowercase sides are directly across from the angles. But I gave you two pieces of information here. B is 70, and C is 10, lowercase c, 10 units. Solve the triangle means you have to figure out what angle A is, and you have to figure out what B and little a are. So how do you think we do it? So one thing is you can get this angle pretty quick by using the fact that the angles in a triangle have to add up to 180. Right? So that's got no trig in it at all. That's like, I want to say first grade geometry, but I'm sure that's not right. So at some point in time, after you learn how to add things to 180, you learn that angles in a triangle add to 180. So you can solve for angle A by saying A plus 70 plus 90 has to equal 180. So this is 160. So A equals 20 degrees. But now we need some trig. So where do I have to go after this? Sine or cosine. Right? The idea is you know the hypotenuse. I've given you the hypotenuse. I guess if you really want to, you can use secant or cosecant, but that would be more work we need to do. I've given you the hypotenuse, and I want to know both the adjacent, well, depending on which angle you look at, say we look at angle A, I want to know both the adjacent and the opposite. So let's solve for little a first. What kind of trig argument could you set up? Sine of 20 degrees should equal what over what? Yeah, whatever you're missing, the opposite side, which we call A, over the hypotenuse. Right, sine is forever and always opposite over adjacent, or I'm sorry, opposite over hypotenuse. So if I apply that definition here, I could do sine of 20 equals A over 10. And then you can solve for A by multiplying over 10. This is where I need your help. Make sure you're in degrees mode.
3.42.
Give me 4 decimal places.
3.4202.
3.4202 or 8?
3.
3.4202. Confirmation? You guys agree? Then by democracy, this is the side length A. But we didn't get a majority, so not really democracy. Yeah, you have to be in degrees because the information was given in degrees. If you're in radians, you'll be way off. What else? I mean, this gets me A. I'm done with A. I need to move on and do B. But just because I'm an overachiever, what else could I have set up to solve for A? Say I wanted to use cosine instead of sine. What could I have done? So if you wanted to use cosine to solve for A, you would have to use this angle instead, right? Because A is adjacent to 70. So you could use cosine. You would just do cosine of 70 equals A over 10. And it'll give you the same answer. So there's usually, if you know both of these angles, then there's 2 trig functions, well 4 trig functions for you to use. Because like I said, you could use secant or cosecant as well, but I wouldn't ever use those unless I absolutely have to. Now, What about for B? Little b. Now there's two routes, there's two distinctly different routes to go here. You can either set up another trig argument, or now that you know little a, you could actually do Pythagorean theorem, right? Because you know two sides of your right triangle, so you can solve for the third. Which method do you think is better? The trig is better because you rounded to get a. So if you use a in your next calculation, you're propagating that rounding error. Right? You're going to get more error if you use this in your next calculation. Whereas if you use a trig argument to get b, and say you use 70 degrees, the given information, so you set up sine of 70 equals b over 10, you're not using a, so you're not doing as much rounding. In some sense. So this is what I would set up to get little b. What do you get? 9.396. 69. I am not responsible for any rounding error, okay? If people aren't rounding up or down, it's not my fault. So then we have all the information that we could possibly want in this right triangle. This is basically what we did, I don't know, in the first section we ever talked about. Okay, this is okay. The only thing slightly new here, slightly new, just slightly, is in this next example. So let's look at this guy. Now I give you a right triangle, but in this case I give you little a and little b. Right, so A, B, C, little a, little b, c. I tell you little a is 7, little b is 24, find the rest. So I need to know this angle, and this hypotenuse. See, we can't use our trick subtracting from 180 yet. Right? So when we have two unknown angles, we have to be a little more clever about it. However, being that we have two side lengths and we're missing the hypotenuse, we can solve for this right away.
25?
Yeah, you can use the Pythagorean theorem. This is a special triple. So for little c, you would do 7 squared plus 24 squared equals c squared, which ends up giving you c equals 25 when you add these in square root.
So now we just solve the theta?
So now, right, we're going to set up a trig argument to solve for a and b. Let's do a first. So if I want to solve for big A, what kind of trig argument can I set up for this angle here? Any one I like, really. So pick your favorite trig function.
Tan inverse.
So let me use sine. Sine of A should equal what? Opposite over hypotenuse. Sine is for always and forever and always opposite over hypotenuse. But I don't actually want anything over here. I want this angle. So how do I get rid of sine? Sine inverse. So because I'm trying to get an angle, I'm going to have to sine inverse both sides. And now you turn to your handy-dandy calculator. Do you want to be in degrees or radians here? I guess degrees. Actually, the problem didn't specify because I didn't give you any angle measures, right? So you could give me either answer, I guess. But usually in these right triangle problems, we're using degrees. So give me degrees.
16.
16 point
2602.
2602
Yeah.
degrees. And what about for B? What would you do?
Just add 16 to 90 degrees.
Yeah, so for B, you can either set up another argument, right? You could do sine of B, for example, equals 24 over 25. But you're going to have to round when you do sine inverse anyway. So it's going to give you the same amount of rounding error whether you do it this way or you just say that 16 plus 2602 plus B plus 90 has to equal 180, right? If you just add them all up and set it equal to 180, this is going to give you the same amount of error. So you might as well do this one. This is really easy. I think I did that right.
73. About 73.
73?
Yeah.
Oh, I did that wrong. Oh, yes. This is like 7, not like 4. Cool. Degrees. If I don't put degrees, then it means radians. So I put degrees. So if you're given two sides, you do Pythagorean theorem first, and then you can do sine inverse or cosine inverse or any inverse to your angle. If you're given an angle and a side, then you can subtract from 180 first, and then do sine and cosine to get your other sides. But those are really the only two situations you can have. You'll do a couple of problems like I gave you before on your review, which is about angle of elevation, angle of depression, those kind of things. Go ahead and try it on the homework and bug me about it. I don't have any examples ready, so if you find anything that's difficult in the few word problems you have, just let me know and we can do it next time. This is the math. Okay, let's do bearings. So bearings are used to describe a direction, and they're kind of picky. All right, so the language of bearings is slightly strict, so you have to be careful. So for example, if you leave a port on a bearing of, see up there where it says N 30 degrees E, what that means is 30 degrees east of due north. So if I write N 30 E, this is read kind of ignoring the N at first and just saying 30 degrees east of directly north. So then you come back and read this guy. So let me draw a couple of bearings, a couple of angles that you can get from these bearings to make sure we have this down before we do a more complicated example. So draw an arrow starting from the origin, pointing in the direction of the described by each bearing. So if I wanted you to draw me an arrow indicating where 50 degrees east of north, so N 50 degrees E, 50 degrees east of north, how would you draw that, you think? So first we have to agree upon a labeling of north, east, south, west, okay? So we're usually going to put, I mean, you can label these however you want, but probably this is the most common way you'll see.
So you would go 50 degrees to east.
So, yeah, so this guy is 50 degrees east of north. So you'll start at north and then go 50 degrees to the east. So like this. The problem is that this isn't usually how we describe our angles, right? Because in standard position, we like our angles starting from the x-axis. So in a lot of cases, you're going to have to convert this to a reference angle, which is this angle here. What's the reference angle here? 40 degrees. So if you're not careful, and you just use the number given in the bearing for your calculations, you'll be off. So you really want to get a picture down so you know where you're heading. So what about the next one here? I want S10W, so 10 degrees west of south. So you start south, and you go 10 degrees to the west. So we write it down. Yeah, so the reference angle, which is the acute angle formed with the x-axis, will be 80 degrees. Now, depending on where you get your bearings from, you know, planes use bearings, boats use bearings, GPS uses bearings, latitude and longitude. This is a lot like latitude and longitude, which is where the idea comes from. But some bearing readings will only deal with north. They'll only reference north. And then it'll just say up to 180 degrees east of north or up to 180 degrees west of north. Okay. But in some other cases, you can other books or other, like other fields of studies use both north and south. So this guy is using south as a reference instead. Right? So ideally, the way this works is if you land in the first or the second quadrant, you'll reference north because you're closer to north. Right? Whereas if you land in the third or the fourth quadrant, you'll reference south because you're closer to south. But it doesn't matter. What's most important is that they're not giving you the angle that you're used to. Okay? They're not giving you this reference angle. They're giving you this angle. The last one. Involving something slip. And 75 degrees W. So 75 degrees west of north. So what quadrant am I in? Second. You start at north, go 75 degrees. So this is the direction I'm heading. What's my reference angle? 15. Right, it's the leftover out of 90 here. Alright, let's try slightly more complicated. So a boat leaves the entrance to a harbor and travels 40 miles on a bearing of 64 degrees east of south. How many miles south and how many miles east from the harbor has the boat traveled? So a boat leaves the entrance to a harbor and travels 40 miles on a bearing 64 degrees east of south. So I need to get a picture. I'm all about the picture. What quadrant am I in? Fourth. Right? Because you need to go, you start from south, your reference direction is south, and you go 64 degrees to the east. And that actually gives you a little bit more information. It tells you how far we travel along that bearing. So it says we travel 40 miles along this bearing. So I'm going to label this distance here 40 miles. Now, you can, what's the question asking? How many miles south and how many miles east from the harbor has the boat traveled? So basically it wants to know, how far have you gone to the east, how far have you gone to the south? Now, you can really draw your triangle with either axis, okay, but kind of the standard way you're going to see this drawn is always with the x-axis. Everything we do in this class, for the most part, is with the x-axis. So what the question is asking is for those two distances. How far east? How far south? How can we get those? Use your reference angle. What's left over here? Let's see, yeah, looks like 26 degrees left over. So then if I want to know my east miles, how far I traveled to the east, I set up a trig function that has x involved. So to solve for x, what trig function should I use? Right, so I have hypotenuse, and I want adjacent, so set up cosine. Cosine of 26 degrees equals adjacent over hypotenuse. So your east miles equals 40 times cos 26. What do we get?
35.9518.
35.9518. You guys agree? Sweet. So we travel 35.9518 miles to the east. That's part of the question. And then for the south, how many miles south have we traveled? You have to solve for y. So what are you going to set up for y? Sine. Right? You need the opposite. You have the hypotenuse. Sine of 26. Solve for y. Sine of 26 degrees should equal y over 40. So 40, when you multiply up, sine 26 should equal y. So y is equal to 17.5. 17.5. That's our miles to the south. It's possible that you'll run into a crazy problem that you can't even set up, in which case feel free to bug me about it. I have no problem doing homework problems on these. But other than that, what's going to trip you up is using the wrong angle here. Okay, so just make sure when you draw your triangle, make sure you use the right angle. The bearing is always measured with the north or the south, so it's not the angle you're used to getting. Questions? No? Okay. Simple harmonic motion. Simple harmonic motion. So the idea behind simple harmonic motion, I talk about a guitar string. If you imagine a point on a guitar string, when you pluck the string, that point is going to oscillate up and down. It's going to keep going up and down, up and down, up and down, up and down. And if you imagine that there's no friction or air resistance or anything dampening the force, then that point will oscillate up and down, up and down, up and down forever. Okay, so that's kind of the idea of simple harmonic motion. Is if you neglect air resistance or friction or anything that's going to stop something from moving, simple harmonic motion is this motion where you just go up and down forever. Okay? And it's modeled by sine and cosine, right? Because sine and cosine oscillate up and down forever. To give you kind of a better picture, let me turn to not me. So another way to describe simple harmonic motion is by a spring and a mass. So if you imagine a tiny mass strapped to a spring, right? And what you're going to do is you're going to pull the mass down or push it up, and then you're going to measure how far it oscillates from zero. Then as time goes on, right, when time t equals 0, if you pull the mass down at time t equals 0, maybe in this case it says -4, as you pull the mass down, you might be down at -4. And then as it goes up, right, once you let it go, the spring will pull it back up, and it'll get to a height of +4, then it'll go back down to -4, and if there's nothing stopping it, it'll just do that forever. So as you can see, this looks like, I don't know, what kind of function do you think that looks like?
Sine.
Sine or cosine. In this particular case, I would probably call that a cosine function. Why do you think that is?
It's at a minimum.
Yeah, it starts at a minimum, right? Sine always starts at a 0, and cosine starts at a max or a min. But if you treat t like your angle, okay, so you're thinking of time as your angle, then or like x, time is like x. Then at x equals 0, at time equals 0, you're down at the minimum. So this is probably a cosine. If when x equals 0, when time equals 0, you were at equilibrium, you were at rest here, then you would use a sine function to model. Let me give you sort of the formal vocabulary here. So an object that moves up and down over time along the y-axis is said to be in simple harmonic motion. If its distance from the origin at any time t is given by one of these formulas. So an object So an object in simple harmonic motion is going to follow one of the formulas d equals a cos omega t, or d equals a sine omega t. just like before, A is going to talk about the amplitude of the object. Technically, A, the amplitude is the absolute value of A. And that just describes how far up and down the object is going to go from equilibrium. So what you have in your head is this picture of kind of the y-axis where this is 0. Right? You have a spring hanging down here with a mass on it. And this guy's going to oscillate up and down, up and down, up and down, up and down over time. And this A is how far it actually goes up and down. Now, omega, what do you think omega is going to tell you?
Compressions.
So omega tells you how much the cosine or sine wave has been stretched or shrank. And what does that have to relate to? The period. So omega is going to give you a way to get the period. So omega is related to the period. Usually the period in these kind of applications takes on the variable capital T. And the formula for period, normally we have the formula period equals 2 pi over b. But in this context, we want to use omega, and then we want to use this letter capital T. So now we're going to say our formula is T equals 2 pi over omega. So omega is related to the period. It tells you how much you've been stretched or shrunk. And the formula is you take 2 pi and divide it by omega. And time is like, that's your input. T, this little t, this is your, like your angle, your input. So then the only other, well, there's two other things to point out. One is the difference between sine and cosine. When are you going to use sine and when are you going to use cosine? If your little mass or whatever you're measuring, if it starts at a max or a min, you use cosine. If it starts at rest, if it starts right in the middle, you use sine. So if it starts at 0. So the other thing that comes up here, sometimes you see frequency. Frequency is related to the period. You guys know what frequency is? Have you ever heard that term? So in terms of, let's look at this picture here. Suppose I knew that it took 1/5 of a second to complete this cycle. So starting from a max, going all the way back up to a max took 1/5 of a second. This would be the period. Right? The period is how long it takes for you to repeat. So in this case, the period would be 1/5. The frequency goes the other way. The frequency takes the reciprocal of the period. So in this case, the frequency would be 5. So if the period is 1/5, frequency is 5. What do you think that means? So what this says is you will do 1/5 of a cycle in 1 second. So, oh, I'm sorry, you will do 1 full cycle in 1/5 of a second. You'll do 1 full cycle in 1/5 of a second. The frequency tells you that you'll do 5 cycles in 1 second. So So the frequency is how many cycles you'll do, always compared to 1 unit at a time. So 5 cycles in 1 second means you do 1/5. That means you do 1 cycle in 1/5 seconds. Frequency is the reciprocal of the period. Depending on the problem, they give you one or the other, and you flip it if you need to. So if your period is 10 seconds, right, it takes you 10 seconds to repeat, 10 seconds for 1 full cycle, what would your frequency be? 1/10. Right? So it takes you 10 seconds for 1 full cycle. 1/10 is the frequency, which means you go 1/10 of a cycle in 1 second. Because in 10 seconds you go 1 full cycle, so in 1 second you go 1/10 of a second. So the frequency is always telling you how many cycles you go in 1 second, or 1 minute, or 1 unit of time. So I put your formulas up here. I wrote them all down here too. Let's work on examples. So an object in simple harmonic motion has a frequency of 1/4 cycles per minute and an amplitude of 8 feet. Assuming the object started at rest, express its distance from equilibrium d as a function of time t. So an object in simple harmonic motion has a frequency of 1/4 cycles per minute. So I gave you the frequency. Slow. It's okay. I gave you the amplitude. I told you that its amplitude is 8 feet. Assuming the object started at rest, express its distance from equilibrium, so its distance from 0. Right? Equilibrium is your rest position. Express its distance from equilibrium d as a function of t, time. So first of all, we can use either sine or cosine. Which one do you think we want to use here? Sine. Sine, because it started at rest. So this guy tells us to use sine. Oops, I found my omega. Omega. So d equals a sine omega t. I just now need to figure out a and omega. So how can I, well, a is given. A is 8. Now you have to be a little careful. I didn't tell you, but I didn't tell you in this problem whether I'm starting from rest and then going down, or whether I'm starting from rest and then going up. Since I didn't tell you, you can choose one, right? But you should be aware that both of these are possibilities, unless I specify. So let's assume we're moving in the, we're going up. So we'll use a, we'll give a positive a value to indicate that we have the usual sine function going up. So then d is equal to 8 sine omega t. And how do you solve for omega?
Inverse this frequency.
So you're given frequency. Frequency is going to allow you to get to omega. You can either flip it and get the period, right? If you flip it, then you know the period's 4. And then you can get to omega that way. Or you can just use this formula that frequency is omega over 2 pi. So you can set 1/4 equal to omega over 2 pi. Let's do it like this. T is equal to 4. The period is the reciprocal of the frequency. So the period is 4. Which means that 4 has to equal 2 pi over omega using my usual formula, right? The period is always 2 pi over b, but I call it omega. So when I multiply by omega and divide by 4, omega is equal to pi over 2. Yeah, no.
How does, never mind.
Okay. So I've given you the 3 types of applications and an example of each. In the homework, you're going to get more complicated examples. And I'm putting it on you to try them and let me know which ones you can't figure out. Okay? So on Wednesday or on Monday, I will go ahead and answer any questions you have on the homework. Oh, I still have 15 minutes though, so just calm down. Calm down. So I'm gonna start the law of signs here in a second, but let me take this in, ask some questions. Yeah, sir.
I need a little help with like changing T into W.
Yeah, so here's an example. So an object is in simple harmonic motion. With period 30 seconds. Here's a question. Find the frequency F, and then find omega. So immediately, as soon as you see the period, you know the frequency. If the period is 30, that means T equals 30. And this would be 30 seconds for one cycle. That's one way to think. So then if I wanted the frequency, what would you tell me? The reciprocal, right? So the frequency would be 1 over 30. This is cycles per second. Meaning I do one cycle in 30 seconds, or I do 1/30th of a cycle in 1 second. So the frequency and the period are always related in this way. They're both reciprocals of one another. Then you can either use, to get to omega, which is what we actually need in our formula, right? Omega is the guy we're always going to need in our formula. You can use one of 2 formulas. You can either do the period is equal to 2 pi over omega, or you can do the frequency is equal to omega over 2 pi. Notice the difference between these 2 formulas is just I flipped it. I usually use this one because this is the one I remember from graphing sine and cosine. Right, remember in graphing, we had the formula that the period was equal to 2 pi over p. So this is the same formula, it's just with a t and an omega. So let's use this one. Because the period is 30, we would have to solve 30 equals 2 pi over omega. But omega is my variable, so how do I isolate that guy? Multiply to bring him up, right? So 30 omega equals 2 pi. And then you got to divide. Right, isolate omega. So omega equals pi over 15. So you reduce. So this is what would go in your formula if you were actually finishing this problem. What would be different if we decided to use this formula? How do you use this formula? Frequency equals omega over 2 pi. What would you plug in here?
You do 1 over 30.
You do 1 over 30, because that's the frequency, equals omega over 2 pi. In this one, all you have to do is multiply up the 2 pi. Right, so it saves you a little bit of algebra, I guess. Because you'll get 2 pi over 30 equals omega. So pi over 15.